Επόμενος ομιλητής είναι ο καθηγητής Κωνσταντίνος Τσάλης, ο οποίος γεννήθηκε στην Ελλάδα, σπούδασε φυσική στην Αργεντινή και έλαβε το διδακτορικό του από το Université de Paris. Η ερευνητική του δραστηριότητα εστιάζεται στα πεδία των κρίσιμων φαινομένων, του χάους, των fractals, της μη γραμμικής δυναμικής και των οικονομικών και της δυναμικής πληθυσμών. Το 1988, με μια σειρά άρθρων, πρότεινε τη γενίκευση της εντροπίας Boltzmann-Gibbs. Η γενικευμένη θεωρία ονομάζεται σήμερα Non-Extensive Statistical Mechanics, ενώ η γενικευμένη εντροπία Τσάλης Εντροπή. Έχει πάρει πολλά βραβεία, μεταξύ των οποίων και από το Αριστοτέλειο και από την Ακαδημία Αθηνών. Και ο τίτλος της ομιλίας είναι Non-Additive Entropies and Statistical Mechanics of the Age of Chaos. Σας ακούμε.
Λοιπόν, καλημέρα σας. Είναι ευχαρίστηση μεγάλη. Βλέπω ελληνική νεολαία, γιατί δεν έχουμε πολύ συχνά στην Ελλάδα. Και ευχαριστώ τους οργανωτές και πολύ συγκεκριμένα την καθηγήτρια Αστέρο Προβατά, που κάθε την οποία έχουμε και ένα paper, ένα δύο paper μαζί. Τώρα θα περάσω στα αγγλικά. Η αλήθεια είναι ότι εγώ πάει σε ελληνικό σχολείο. Λοιπόν, δεν τα καταφέρνω να κάνω μια διάλεξη. Λοιπόν, θα περάσουμε στα αγγλικά. Θέλω να μιλήσω. I want to talk about a generalization of the usual Boltzmann-Gibbs statistical mechanics, which normally is a mandatory system all around the world. In physics, chemistry, computational sciences, many engineerings, and I will try to present to you a relatively recent generalization of that basic theory in physics. So let me start with these words by Ettore Majorana, who was a young collaborator of Enrico Fermi. And he wrote in 1942, he talked about entropy. And he said this is mainly because entropy is an additive quantity as the other ones. In other words, the entropy of a system composed of several independent parts is equal to the sum of entropy of each single part. And then he says, equal probability is a new hypothesis which might be violated in some occasions. Under this hypothesis, and then he works out the usual Boltzmann-Gibbs statistical mechanics. Under this hypothesis. This is the hypothesis we're going to violate, and therefore we're going to generalize statistical mechanics. Here you have a table of entropies. Here you have minus sum of P log P, where P are probabilities. And this is the famous Boltzmann-Gibbs von Neumann Shannon entropy that I will call just Boltzmann-Gibbs entropy or just Boltzmann entropy. If the probabilities are all equal, we obtain this celebrated formula, which is on the gravestone of Ludwig Boltzmann in the Central Cemetery in Vienna. But I'm going to talk mainly about this line, where you immediately realize there is an extra index, Q. If in this line you take Q equal 1, or Q going to 1, you recover this line. And therefore, I'm not exactly presenting an alternative. I am presenting a generalization of the usual entropy. I'm going to present basically a generalization, since the usual expressions of entropy are contained as a particular case, Q equal 1. Now, this expression and this expression, which is a particular case of this, have a lot of common properties, such as concavity, extensivity, many of them. And of course, they must differ in something. If you want to generalize something, you have to violate at least one property that you are generalizing. Because the only expression that violates no property at all is P log P, and you did not generalize. So if you want to generalize, you are going necessarily to violate something. We are going to violate here additivity. And I will come back onto that. This expression is additive, whereas this expression is non-additive. And you will see that this introduces a very important difference, not only conceptually, but also in the applications, in the consequences. So the table that you just saw can be rewritten in a more elegant, in a more compact way by introducing this definition. Q logarithm of x equal this object here. And if you take q going to 1, you recover the usual logarithm. The inverse function is the q exponential, which you see here. And if you take q going to 1, you're going to recover the usual exponential. These functions appear all the time in this theory and in their applications. And therefore, in particular, the table that you just saw can be rewritten in a more elegant way: logarithm, logarithm, q logarithm, q logarithm. And a mathematician said once that well represented, half solved. So a good representation helps a lot. So I'm going to talk a lot about q exponentials, q Gaussians, which is q exponential of minus x squared, q logarithm, etc., q functions. Now, where that particular expression of entropy comes from, I mean this expression, where it comes from? Well, the rationale was very simple. In fact, what I wanted to do was to put a bias onto probability. So instead of talking about probability, we will start talking about powers of the probability. So if q is below 1, this quantity is larger than this quantity. If q is above 1, it's the other way around. And if q equals 1, then this quantity is equal to this quantity, and this is precisely Boltzmann-Gibbs entropy, Boltzmann-Gibbs statistical mechanics, where there is no bias. So why introducing a bias? For example, in the Iguazu Falls, in the frontier between Brazil and Argentina, it's a fantastic chaos of water going in all directions. And nevertheless, in the bottom, there is the river, Iguazu River. And there you have slow vortex. In spite of the tremendous chaos around, there are in the bottom of the river slow vortex, very stable. And it's amazing to think, how come this simple low probability configuration can live together with the tremendous chaos of Iguazu Falls. So the idea was precisely to put a bias on the probability so that controlling Q, you control the weight of the probabilities. So we want to use P power Q. The simplest permutation invariant form is the sum, because A plus B is the same like B plus A. Then, okay, we are going to adopt a function of the sum. What function? Let us start with the simplest one, a linear function, A plus B times this. Now, this entropy has to be zero if you know everything, because entropy is the lack of knowledge. So if you know everything, you have no lack of knowledge, so the entropy must be zero. When you impose this for any reasonable entropy should satisfy this, you obtain A equal minus B. So you get this form. And now, the simplest way to recover Boltzmann-Gibbs particular case for Q equal 1 is to assume this constant to be Boltzmann constant divided by Q minus 1. And we are done. That's it. So the intuition is just at this level. The rest is very trivial mathematical arguments. Now, a question appears: are there senses in which SQ is unique? Because when you have a mathematical function, you can generalize it in 1,000,000 different ways. And here, we're generalizing in one particular one of these 1,000,000. So why that one? So are there senses in which SQ is unique? Yes, many. And I will concentrate on this recent one, Enciso Tempesta. Those are two mathematical physicists from Madrid, in Spain. And they use in their uniqueness theorem two properties, trace form and composability. An entropic functional is said to be trace form if you can write it as the sum of some function of probabilities. If you do this, you can immediately arrive to a generalized logarithm. And this quantity here, you can call it surprise, like Watanabe, or unexpectedness, like Barlow, a physiologist. Why? Because suppose the normal logarithm. If you know that something is going to happen, when it happens, you have no surprise. So you know this is going to go down. I leave it, it goes down. No surprise, we knew it. So when the probability equals 1, the surprise is logarithm of 1, which is 0. Now, if you play at the lottery, the probability that you win is nearly 0. You know that. But it is possible that you win. If you win, you have a fantastic surprise. Because when the probability goes to 0, the surprise goes to infinity. So this concept of surprise or unexpectedness is very interesting, but it appears only if the entropy can be written as a sum of some function of the probabilities. Composability is a different issue. It is deeply related to thermodynamics. If you have a system A, which is independent from system B, and you know the entropy of A and the entropy of B, can you predict the entropy of A plus B? If you can, you will say that that entropic functional is composable. If you think about nutritionists, they tell you, if you eat an ice cream of 100 calories, and you eat a souvlaki of 200 calories, you are getting inside the sum, 300 calories. The nutritionist knows not much about molecules, about atoms, about quantum states, about internal energy. Normally they know nearly nothing about that. But they do know that if you eat an ice cream 100 calories plus a souvlaki 200 calories, they do know how to compose them. You are getting inside 300 calories. This is at the very bottom, at the very deep level of thermodynamics, where you can say a lot of things without knowing the microscopic details. An entropic functional which satisfies this will be said composable. And that uniqueness theorem of Enciso Tempesta, he is a physicist, that one in fact is a mathematician. They proved that SQ is the unique entropic functional which simultaneously is trace form, composable, and has Boltzmann entropy as a particular case. So you have this diagram. Here you have trace form entropies. Today in the literature, there are over 50 entropies. When I started working with that 34 years ago, there were only a couple of them. But today there are 50, over 50. So you can classify them. Many of them are trace form. Many of them are composable. Many of them contain Boltzmann entropy as a particular case. But only one satisfies the three properties simultaneously, and that's SQ, which of course contains for Q equal 1 Boltzmann entropy. So this is an interesting theorem of uniqueness that is in the bottom of an argument that we could develop with Hans Haubold from Vienna, analyzing that paper, 1910, by Einstein. So Einstein wrote this expression, Boltzmann expression, as his equation number 1. And he says here in German that the relation between S and W in equation 1 is the only reasonable given the proposition that the entropy of a system consisting of subsystems is equal to the sum of entropies of the subsystems. So under the hypothesis of additivity, under this hypothesis, then Boltzmann formula is the only reasonable one. This is what Einstein said. On this basis, as I mentioned to you with Hans Haubold, we analyzed a requirement of Einstein for entropies. And his requirement is this one. The likelihood function of A plus B when A and B are independent must be the product of the likelihood functions. This is what sometimes is called Einstein principle, Einstein likelihood principle. Einstein has a lot of principles, right? Well, this is one more. And this principle, the proof is basically here. If you use Boltzmann entropy, which is logarithm of W, you make the Einstein inversion of this, and you get the likelihood function proportional to the exponential of the entropy. And if you have this, if you impose that expression to A plus B, it is the sum of the entropy of A plus the entropy of B. This is the product, and you get the requirement of factorizability. This is equal to the product. You say, okay, that's a nice mathematical property, and so what? So what that it is very, very important. Because of this property, sciences exist. A cardiologist does not need to know everything that Astero Provata knows to do cardiology. It's enough for him to know about the heart, the lungs, the circulatory system, the brain. That's enough. And he can be an excellent cardiologist. So cardiology exists because it is possible to do a lot of things in the realm of cardiology without entering into the details of the nuclear details of this table. It's not necessary. This is what is written. So epistemologically speaking, it's much more than a nice mathematical property. Is the very bottom justification of the existence of different sciences that can be developed independently or almost independently from the other sciences. Well, with Hans Haubold, we could prove that this requirement is satisfied for SQ, not only for Boltzmann entropy, but this entropy for all values of Q. Not only Q equal 1, but also Q equal 1.3. This is satisfied. This is an important basis from the, as I said, epistemological point of view. Now, in that initial slide, there were two words that I will define a little bit more now: additivity and extensivity. So, an entropy is additive according to the definition of Oliver Penrose, 1970, if for any two probabilistically independent systems, A and B, the entropy of the sum equals the sum of the entropies. If it is so, the entropic functional is additive. If not, it is non-additive. You can prove in two lines that SQ, and therefore it is non-additive because it has an extra term. And here, if you cancel K, you arrive to this with this little business here. So this teaches us something interesting. Q equal 1 is equivalent to the Boltzmann constant going to infinity. I will come back onto this. These two concepts, Q different from 1 and K going to infinity, are nearly the same thing. That's additivity. Extensivity is much, much more complicated. Extensivity of a system with a particular entropy is when the entropy is proportional to the number of elements, when it is, thermodynamically speaking, extensive. So, because of this, the nutritionist knows that if you eat 2 ice cream of 100 calories each, the 2 ice creams is 200 calories, the double. Not square root of 2, not 4, just the double. But simple law, that's extensivity. The entire science of nutrition is based on this. Normally they don't know, but there are so many things that are true and we don't know. So no problem. They don't know about thermodynamic extensivity. Nevertheless, their science is based on. Let me now make for you with examples clear the difference between additivity and extensivity, because the two of them have something to do with sums. So they look like the same. They are not the same. They are very different, but they look like the same. So let me gave you a few examples. If the total number of possibilities, of microscopic possibilities of the system increases exponentially with n, like for example, n coins, you will have 2 power n. You must use Boltzmann entropy because the logarithm of this is proportional to n. And therefore, the entropy for this family is extensive. It's okay. It's okay with thermodynamics. We don't want to violate thermodynamics. We have no problem in violating additivity, but we don't want to violate thermodynamics because there is no reason for doing that. Now, if instead of this, if you have a complex system where the total number of possibilities increases like a power of n, and not like an exponential of n. If you use Boltzmann entropy, you're going to take the logarithm of this, and the logarithm of this is proportional to the logarithm of n. We don't want logarithm of n. We want n, which is very different from logarithm of n, and very especially if n is the Avogadro number, which is the number of molecules which exist in the air in this room. So, for this family, Boltzmann entropy does not work. But if you take SQ, ακόμα πιο κοντά, θα χάσω την πείνα, διότι θα το φάω αυτό εδώ. Λοιπόν, εδώ, αν μεταχειριζόμαστε, if we use Boltzmann entropy, we are going to take the logarithm of this, which is going to be proportional to n. Sorry, proportional to logarithm of n. But if you take SQ with Q equal 1 minus 1 divided by rho, the same rho that you see here, that one is proportional to n. That's okay for thermodynamics. Not Boltzmann, but SQ. If you have a stretch exponential, SQ does not work for any value of Q. So you must use a different entropy. There is such an entropy in the literature. You have it here. And it is proportional to n when delta is equal to 1 divided by gamma, the same gamma that you see here. And another example, if the number of possibilities increases logarithmically with n, the same structure appears with another entropic function. So here you have a remark. Mu power n is much larger than this, which is much larger than this, which is much larger than this, and that one is full occupancy of phase space. Because mu power n is n times n times n times n times n times n. So this is the entire Lebesgue measure of the phase space. All microscopic possibilities are taken into account. So all the others have zero Lebesgue measure. They are like hierarchical fractals, structures, like a fractal, like a multifractal. A fractal has, for example, tiny points, infinite number of tiny points, is not zero. It's a lot, it's an infinite number of tiny dots. But its Lebesgue measure is zero. So if you want to do entropy and statistical mechanics of such a system, you have to take this into account, because these numbers and these are much smaller than this. So in this table, you have a summary of what I just said. Boltzmann entropy is additive. That's it, no problem. SQ is non-additive. The S delta that I mentioned is non-additive. The S lambda that I mentioned is non-additive. Perfect. And here you have families of systems. If you have this family, you must use Boltzmann entropy because it is extensive. And you must not use SQ or S delta or something else. You must use normal entropy and normal statistical mechanics. But if you have this family, then Boltzmann entropy is non-extensive, not good. But that one is extensive, fine. And the other two are non-extensive, not good. If you have this family, you must use this. If you have this family, you must use this, and so on. So, if you married with Boltzmann, you will live here until the death separates you. But let me tell you, there is a better marriage, to marriage thermodynamics, to marriage Clausius. And then you will live here until the death separates you. This is my case. I worked in my doctorate degree and many years along this. But then I realized that it didn't work for complex systems. And now I prefer this. Here you can say, well, if you violated additivity, why don't you violate thermodynamics as well? Since you are on a mood of violation, just violate everything that is around. No, it's not like that. Theoretical physics has to violate something if there is a reason. If there is no reason at all, you don't violate all kinds of properties because it's not anymore theoretical physics. It's mathematics. It can be very interesting, but it's not theoretical physics. So we see no reason for violating thermodynamics, but I'm showing to you that there are reasons for violating additivity of the entropy. And in particular, you have these lines by Albert Einstein, where he says, a theory is the more impressive, the great the simplicity of its premises is, the more different kinds of things it relates, and the more extended is its area of applicability. Therefore, thermodynamics will never be overthrown. So Einstein, and practically almost 100% of physicists in the world, they don't violate thermodynamics. They don't violate the first principle, which is conservation of energy. They don't violate the second principle, which is the heart of irreversibility and the heart of birth and death. So they don't violate thermodynamics because up to today, there is no strong reason to violate thermodynamics. Here you have a metaphor. Aristotle used to say, metaphors of all things the greatest. So let us make a metaphor here. Here you have the composition of velocities of Galileo. So if the train goes 100 kilometers per hour, and on top of the train you walk at 10 kilometers per hour, you go to 110 kilometers per hour with respect to the land outside. Very simple, just a sum. You do it by heart. But then Mr. Herr Professor Albert Einstein, he arrives and he says, no, this is wrong. This is true. Einstein destroyed the beautiful additivity of composition of velocities of Galileo. Why he did that? He didn't like additivity? Yeah, he liked as anybody else. Anybody likes to do a small calculation by heart. But if you have velocities here, 100 kilometers per hour plus 10 here, you have to do it with a little computer. So no doubt Galileo was more beautiful. So why Einstein did that? because he had a superior goal. He wanted to unify electromagnetism, Maxwell equations, and mechanics in a single formalism. And when he tried to do that, discovered he had to use Lorentz transformation and not Galilean transformation. And when he did that, he discovered that the composition of velocities is a little bit ugly, not beautiful like Galileo. But then Einstein said, okay, I paid that price. That's a small price compared to unifying electromagnetism and mechanics. So in non-additive entropies and non-extensive statistical mechanics, etc., you pay a price. You violate the beautiful additivity of Boltzmann expression because you have a more important goal. You don't want to violate thermodynamics. You want to satisfy thermodynamics, and if for this it is necessary to give up of entropic additivity, you give up. That's the philosophy of what I'm talking to you. Here about the four contemporary constants, physical constants of nowadays of contemporary physics. You have H, G, C, and K. So if this is different from zero, you go from Newtonian mechanics to special relativity of Einstein, 1905. And to do that, you use the fact that the Galileo transformation becomes Lorentz transformation. If G is different from zero, you go from special relativity to general relativity. And something very funny happens. Space-time curves according to the masses that are around. If you take H different from zero, you go from Newtonian mechanics to quantum mechanics. Something very funny happens. You cannot measure position and velocity simultaneously. You must choose one or the other, not the two of them simultaneously with infinite precision. And finally, when this is different from zero, you go from Boltzmann-Gibbs statistical mechanics to non-extensive statistical mechanics because something happened, something funny is happening. The entropic additivity is lost. Like here, the Euclidean geometry is lost. Now, let me show to you something interesting about the history of science. Gibbs, in his book, 1902, he wrote these lines, and he wrote that when you treat the canonical distribution, equation 92 must be finite. And equation 92 is what we call today partition function. So the partition function of what you are calculating must be finite. He says, if not, the law of distribution becomes illusory. What law of distribution? His law of distribution. Gibbs' distribution becomes illusory, says Gibbs, if the partition function is not okay. So you have mathematical constraints for Boltzmann-Gibbs statistical mechanics to be okay. And one of them is the partition function to be finite. And he even gives an example where it doesn't work, which is when a mass attract one another inversely as the squares of their distances, thus Newtonian gravitation. So Gibbs knew that his law, his statistical mechanics, does not work for nothing less than Newtonian gravitation. So Boltzmann-Gibbs statistical mechanics does not work for planetary systems, for a lot of things of astrophysics. It's a big misery that that theory does not work for such important systems. But it doesn't work. And Gibbs knew that. But after him, thousands and thousands of physicists, chemists forgot that. And they thought that Boltzmann entropy and Boltzmann factor, Gibbs factor, was not coming out from a hypothesis. They acted as if it was given by God. In the tables, when Moses came down, there were 10 commandments, and in the back of the table, it was written S equal logarithm of W. They acted as if it was like this, but it was not like this. There is no historical evidence that on the backside of the tables of Moses, it was written Boltzmann entropy. It's an hypothesis. So if you need, you can violate it. That's it. So if you consider long distance interactions, one divided by a distance power alpha, you have alpha here and d here, and you have a bisector. And on this side, the partition function is finite. And on this side, it diverges. And therefore, on this side, you must use Boltzmann-Gibbs statistical mechanics. And on this side, you must do something, because it doesn't work. In particular, the air in this room, the molecules, interact basically through a Lennard-Jones potential. And the Lennard-Jones potential decays like 1 divided the distance power 6, because it's a van der Waals interaction. 6. So the air in this room has alpha equals 6 and d equals 3. So the air in this room is up there, here. No problem. You use Boltzmann-Gibbs statistical mechanics. It's in all the textbooks. But Newtonian gravitation is outside. So I'm talking about this region, the hard region, because the other region is in the textbooks. Maybe I will skip this. These are Legendre structure arguments that thermodynamics has to always have an extensive entropy. Energy can be non-extensive. The temperature can be non-intensive. You can have various things, but entropy is always extensive, no matter the range of interaction, no matter the ratio alpha divided by d, no matter if you are here or here. Entropy must be extensive. Otherwise, you are violating thermodynamics, and we said we don't want to violate thermodynamics. Not because it was written in the back side also of Moses' tables. Not because of that, because we see no physical reason, what we know about the world, to violate thermodynamics. Just because of that, we don't want to violate. I will skip this and let me go here. One of the most important things in theory of probabilities is the central limit theorem, which says that if you add n independent random variables, the sum is described by a Gaussian. So it is called the central limit theorem because it is the most important theorem of theory of probabilities. And because of that theorem, in nature, there are hundreds, thousands of Gaussians because of that theorem. So if a lady comes in with Chanel 5, in a little while we smell Chanel 5. What happened? It happened Brownian motion of the aromatic molecules, and with convection, etc., it arrived to your nose, and all this is described by normal diffusion, which is Gaussian. So this is why you smell, because there are Gaussians. If you analyze the height of people, you get Gaussian distributions. If you analyze the darkness of the skin, the concentration of melanin, you roughly have Gaussians. So plenty of Gaussians in the world because of the central limit theorem. But it happens, and you will see, there are more and more Q Gaussians being discovered. And why there are so many Q Gaussians in nature? Then we need a generalized central limit theorem to understand why there are so many Q Gaussians. And this is what we did with two pure mathematicians and the mythic Murray Gell-Mann, who died a few years ago and who won the Nobel Prize in Physics, and who invented the word quarks. So inside protons and neutrons, you have quarks and gluons, and the quarks are charm, top, bottom, etc. All this was invented by Murray Gell-Mann, who worked with us, and we generalized two important theorems of theory of probabilities. So in this table, you have the structure of the outcome. Just the structure, because the proofs would take us not less than 1 week of lectures. But the structure is very simple. Here you have Q equal 1. If this means that the variables that you are summing are independent. And then if the variance is finite, the attractor is a Gaussian, as I said. If the variance diverges with some mathematical delicacies, the attractor is not a Gaussian anymore, it's a Levy distribution. Okay, these two theorems are in any reasonably good book of theory of probability. What we did was add these two theorems with Q different from 1. Here you have Q Gaussians as attractors, and here you have what we named Q alpha stable distributions. But the important one is this one. And because of this theorem, there are so many Q Gaussians in nature. So, sign. Yeah. Maybe I will skip that one. It's not so important, the present context. But now you see that in everything that I was talking of an index Q. Where does it come from? How do we know the value of Q? Q is what? Is a fitting parameter? Is something fundamental? Where is it hidden, Q? How do we find Q? Well, it is hidden in the microscopic dynamics of the system, either classical, quantum, relativistic, it doesn't matter. It's from first principle reasoning that you get the value of Q. And an example is this paper with Filippo Caruso when he was doing his doctoral degree in Scuola Normale Superiore di Pisa. And we obtained for one-dimensional systems at 0 temperature, we obtain Q as a function of the inverse of the central charge. This here is not the speed of light. This is the central charge, which appears in quantum field theory. One of the speakers before the interval mentioned Young-Mills field theory, where it comes from things like that. And here you have the expression, Q as a function of the central charge, a very nice expression, and here you have the representation, and when the central charge goes to infinity, Q goes very lovely to 1. So, as I told you, we're not putting Boltzmann-Gibbs entropy into garbage. We are generalizing it. So we have a line, and this line contains Q equal 1 as a particular very important case. Another example happens in the logistic map that many of you might know. Here, at the edge of chaos, different from here where you have strong chaos. At the edge of chaos, you have weak chaos. Here is the so-called Feigenbaum point. And at that point, it is possible to calculate Q. And here you have it. This relation came from a scaling argument by Marcelo Lira and myself many years ago in Brazil. But this relates Q to the celebrated universal constant alpha of Feigenbaum. And alpha Feigenbaum is known with 1,000 digits. And a German young man calculated these 1,000 digits. We put this into this formula and we got Q with 1,000 digits from first principles, not from fitting. There is nobody in the world that can produce 1,000 meaningful digits with fitting. He would deserve not one Nobel Prize, he would deserve a dozen of Nobel Prizes. Somebody who fitting would produce 1,000 meaningful digits. So this is from first principles. When you can do it, and what if you cannot do it? If you cannot calculate it, it is there, but you cannot calculate it. Then you can fit the value of Q. Not because the theory demands Q to be a fitting parameter. The theory demands Q to be a first principle index. But if you are unable to calculate it for your specific system, then you do what you can. In that case, you can use Q as a fitting parameter. In this example, that was produced by Ugur Tirnakli from Turkey and Ernesto Borges from Brazil, and they analyzed an important two-dimensional map. Here you have it, X and P. And this map has one control parameter, K, and for any value of K, this map is area preserving. It's not dissipative, it's not creative, it's area preserving. It's like a small Hamiltonian. So for this small Hamiltonian, they studied what happens, and they obtained that when K is large, see the K that you see here, when it is large, for example, 10, and you sum the successive iterations of X, you have a beautiful Gaussian. When you have strong chaos, you have a Gaussian. And that's Boltzmann-Gibbs statistical mechanics. But when you have a small value of Q, the system does not like Gaussians. It's not you who does not like, it's the system. His nonlinearity, his dynamics do not like Gaussians when K is very small. And it was proved 1 year, 2 years ago by Buntis from Patras, Verman from United States, and Vivaldi from Queen Mary College. It was proved that the exact value of Q is not 1, it is 2. So you don't have Gaussians. You have Q Gaussians. That's it. Validity and failure of the Boltzmann weight. Here you have an example. If you consider a d-dimensional XY model, which is a magnetism, and I know this in one of the slides before me this morning, somebody talked about magnetic systems. So XY is a magnetic system. If you consider a classical version with an inertial term, when alpha divided by d is below 1, I told you Boltzmann-Gibbs statistical mechanics does not work. So here you have an example, alpha divided by d equals 0.9. So it shouldn't work, Boltzmann-Gibbs, and it doesn't work. Here you have the Maxwellian distribution of velocities. Maxwellian. It doesn't like Maxwellian. In the textbooks, it is written that the distribution of velocities is Maxwellian. They forget to tell you if the interactions are short-ranged. If the interactions are long-ranged, maybe it's not Gaussian. And this is what happens here. Alpha divided by d equal 0.9. For d equal 1, 2, 3, they are all collapsed here, and it's not a Gaussian. And what about the distribution of energies? It's not an exponential. This is what Gibbs wrote in 1902, the canonical law, the exponential. You see, log linear, a straight line. So this is Gibbs' factor. He said it might be illusory, and it is. Here, for alpha divided by d smaller than 1, it doesn't like Boltzmann-Gibbs factor. It likes this, and this is a Q exponential. Okay, this is theoreticians playing around with computer scientists or computational physicists with computers, but nature is something different. Nature is outside or inside, but not in the computer. So these people from France, they verified in granular media, they verified a few years ago in Grenoble, this law. Alpha, which has to do with anomalous diffusion, not the alpha I was talking before. This is here. The exponent of anomalous diffusion must be equal to 2 divided by 3 minus q. This law was predicted by a young Dutch, Dirk Jan Boekman, and myself many years ago. It remained as a prediction, and it was validated, it was verified by France. 19 years later. It took 19 years to verify the prediction. And when it was verified, we were very happy, of course. We were waiting 19 years. So when it comes, you say, oh, that's great. This verification was so important that it was chosen by the editors of physical regulators as an editor suggestion. This symbol means that the editors are suggesting the readers to read this paper. Now, it was mentioned here a little bit earlier, CMS and Atlas, but around the LHC there are 4 big detectors. In all these detectors, they work like 4,000 scientists, engineers, etc. And at some occasion, they invited me to visit CERN because they were organizing a workshop, successive years. Q entropy and Q statistics, etc. So they invited me, I went there, and they took me down in the Alice detector. So we went down, and here, 80 meters down, or 100 meters down, they offered to me a coffee. And so I thought the first time in my life I'm drinking a coffee 100 meters below Earth. Everything looked like a film of James Bond there. So they made me visit the detector, and the detector you can see here, you see a person here. And this detector has a door, which you see here. And the guy that was guiding me with special optics and ears and connected, I don't know where, to avoid people, terrorists, to put bombs there, etc. Then when we arrived to the door, he told me, what is the weight of the door, in your opinion? Oh, I looked at the door. I said, I don't know, many tons. He said, it is heavier than the Eiffel Tower. I said, you are kidding. This door is heavier than the Eiffel Tower? He said, yes. And it takes 2 days to close it. I said, my God, I never saw a door like this. Can you take a photograph of me? And they took me a photograph with a door that is heavier than the Eiffel Tower. So why I'm showing this to you? Because here you have their results. This is the distribution of probabilities as a function of the transverse momentum in CMS, Atlas, Alice, different energies. And here you have 14 decades. You know what is 14 decades? It's a precision of 0.0000000, 14 zeros, and then 1. That's 14 decades. And you see the experimental data, and you see these nice curves. And these nice curves are just Q exponential, with Q equal 1.14. So here, there are various interesting features. The first of all is the talent of these experimentalists that in a single experiment, they can check 14 experimental decades. For the fair, as French people say, not trivial at all. They succeeded that. And another relevant feature is this very simple expression, a Q exponential of this, goes, okay, all the way down. In the straight part, but also in the belly, everywhere. For you to compare, this is Q equal 1. So here, Boltzmann-Gibbs is okay. But here, Boltzmann-Gibbs is millions of times wrong. Billions of times wrong here. And Q is just a little bit above 1. Instead of 1, it is 1.14. It's enough for high energies to be billions of times wrong. Very impressive. And Walton and Rafelsky, theoretician of quantum chromodynamics, he calculated many years ago a value of Q, and he got Q equal 1.11. And here is Q equal 1. And the data fit with Q equal 1.11. They don't fit with Q equal 1. That was his physical regulators 20 years ago. And 2 years ago, these three people, two from Spain, two from Brazil. That one is the present president of the Brazilian Physical Society, the first time a woman became president of the Brazilian Physical Society. And that one is from Spain. And they used the young Mills field theory that was mentioned earlier. And in the approximation of one loop within quantum chromodynamics, they obtained a beautiful first principle expression of Q. Q is function of the number of colors and the number of flavors. And when you put 3 colors and 6 flavors, you obtain Q equal 8 divided by 7, which is 1.14. 1.14. And here, and also if you put 3 and 3, you obtain 1.11. Finally, I will skip this very recent application, although it is very interesting because it's the celebrated Fourier law of 19th century, which is like Ohm's law, same period, and Fick's law, a little couple of decades later, and Newton's law, a couple of centuries before. I will skip this, and I go to the finite application that it's very interesting. My opinion, it was published 1 year ago by people from Iraq and Malaysia, and they analyzed images of computer tomography with people with COVID-19. And here you have one patient. Here are the 2 lungs. Here you have the fibrosis produced by COVID-19. And here you have the same data handled with Q equals 0.5. And you see much better for the doctor to make a diagnostic. Here you have another patient. Here you have the fibrosis. Here you have with 0.5. A third patient, here you have the fibrosis. Here you have what you see with 2 different lines. And with this, I will finish telling you that a couple of months ago appeared this book with the mathematician, Mathematical Foundations, Non-Extensive Physical Mechanics. And with this, I thank you very much.
Υπάρχουν ερωτήσεις? Any questions?
Ναι, όχι. Όχι. Το logistic map έχει μόνο 2 values of Q. Q equal 1 whenever the Lyapunov exponent is positive. And Q equals 0.2445, the number, when the Lyapunov exponent is 0. Only this value of Q, either 1 or the other, and that's it. It doesn't change between 0.24 to 1, because those are universality classes. It's like this or nothing. Many people put that kind of question because it comes naturally to the mind. Maybe Q changes gradually. No, it doesn't change gradually. It changes suddenly, like a square. If you do a little bit like this, just a little bit, is not a square anymore. It's a rectangle. And the symmetry changed. Just a little bit, everything changed. It's like that.
Ευχαριστήσουμε λοιπόν τον κύριο Τσάλη.